Hello and welcome to the third and final video for Unit 4-2. I guess just to put a pin in the last video, again, we just call that property linearity. Summarized, it says that if f1 and f2 are functions and a and b are constants, so fixed numbers, then the Laplace transform of something like this, so a linear combination essentially of two functions, is the linear combination of their Laplace transforms, if you want to think about it that way. Otherwise, you can just say you split up at plus and minus signs, and the constants factor out. Okay, so let's conclude this page. The first thing we're going to do is show that the Laplace transform of a derivative equals this expression here, s times capital Y of s minus little y of 0. This is on the table of Laplace transforms that you can find either in the previous unit, 4-1, or at the very end of this unit on the next page. So we should probably verify this, so let's go ahead. I think there's one caveat that we need to be mindful of here, and that is that we actually, even though it's kind of being swept under the rug, we're actually going to assume that the Laplace transform of y exists, or like is defined. And the reason for that is it gives us, so therefore, assuming this, we get the following relation, that the limit as, and now I'm going to use the letter n for reasons that you'll probably see in a couple minutes, goes to infinity of e to the minus s times n times y of n equals 0. The reason that this must hold is because if you think about it, what goes inside the integral of the Laplace transform of y? Well, it's this, right? And so if this doesn't go to 0, there is no way that the integral is going to be finite, right? Otherwise, you're going to have infinite area, and so the Laplace transform would not exist. And so I'm not saying that the whole integral goes to 0, just this inside part, what's called the integrand, right? That has to go to 0. Okay, and so that's just a restatement that we're seeing here, right? The integrand is essentially going to 0. All right, so let's compute the Laplace transform of y prime. So we get L y prime. Well, that equals the integral from 0 to infinity, e to the minus st times y prime of t dt. By definition, that's the limit n goes to infinity. Integral 0 to n, e to the minus st y prime of t dt. And now let's make the use of, or excuse me, the integration by parts. So we're going to put u equal to e to the minus st. Du is therefore minus s e to the minus st dt. dv is going to be y prime of t dt. And to get v, you just do the antiderivative. Well, that's just y, right? All right, so we get limit n goes to infinity. And now we do uv minus integral v du. So uv, we get e to the minus st times y of t minus the integral of v du. So we get minus s e to the minus st times y of t dt. And this is integral 0 to n. All right, so let's evaluate. We get limit n, capital N, goes to infinity. Plug in n, you get e to the minus s n y of n. Oh, that looks familiar. Minus e to the 0 times y of 0. And now notice here we have a plus. And furthermore, s with respect to this integral is constant. So I'm actually going to factor out just the s. Okay, e to the 0 is 1, so this is actually just minus y of 0. And furthermore, this limit right here, oh, well that's exactly this limit right here, e to the minus Sn times y of n. As n becomes large, this also goes to 0. And so we get 0 minus y of 0. And now we come over here, plus s. This limit as n goes to infinity of this integral, well, we're just letting n go to infinity here, so this is actually s times integral 0 to infinity e to the minus st y of t dt. And you'll observe that this right here is the definition of capital Y of s. So this is minus y of 0 plus s times capital Y of s. Oh, well, just rewrite that. That is s times capital Y of s minus little y of 0. Okay, so that checks out. And now here, we're just going to use the last exercise to prove that y double prime, that its Laplace transform is given by, well, we can just take a peek below here, given by this expression here, s squared times capital Y of s minus s times little y of 0 minus little y prime of 0. So this is a neat little idea here. So the first thing we're going to do is we're going to let u be y prime. Now let's see what that gets us. That says that then the Laplace transform of y double prime is really just the Laplace transform of u prime, right? Because if u is y prime, then y double prime is u prime. Let's come back above. Oh, we know what the Laplace transform of the derivative is, right? That is right here. The Laplace transform of a derivative is s times the Laplace transform minus, well, that function without the prime of 0, right? So this is s times, and now instead of using capital U of s, I'm just going to write it as L of u. Those two things are the same, minus little u of 0. And the reason I write it like this is because now I'm going to back substitute what u is equal to. Well, that's equal to s times L of y prime minus little u of 0. But again, little u is y prime, so this is s times L of y prime minus y prime of 0. And this is little y prime here, of course. All right, well now let's look above. This is L of y prime, and our answer is way over here, s times capital Y of s minus little y of 0. So just use parentheses, but I think we're almost done, right? So L of y prime gets replaced by, there it is just above next to the check mark, s times capital Y of s minus little y of 0. And now don't forget this minus little y prime of 0. And now just distribute, so you get s squared capital Y of s minus s times little y of 0 minus little y prime of 0. And that's exactly what we have on the chart. So you see that this is a much easier process. Once you have one derivative, you can essentially inductively use that property of the Laplace transform of a derivative to get you the next Laplace transform for the next highest order derivative. This is much easier than, I mean, you could do it the hard way. Let me show you that that's not exactly the best route. What you would do is if you wanted to find L of y double prime, that's the integral 0 to infinity e to the minus st y double prime of t dt. Now you would have to do integration by parts twice, but you can see how messy it gets with integration by parts once, right? Look at all of this. Just imagine how messy that would be doing integration by parts twice. All right. Like I said, the next page, there's just the table again, just for your reference. So hopefully this helps as you start to work on the homework problems.